Hi, this is Mrs. Huntley. You should be on page 13 of your supplemental materials. This is the additional packet that says real number system on the front of it. And our essential question for this lesson is how can I estimate the value of a non-perfect square? This is kind of a review. We did go over this already when we were in the Eureka materials. However, I don't feel that reviewing something is necessarily a bad thing. This lesson is presented slightly differently, so we're actually going to be modifying this lesson a little bit to kind of fit with what Eureka was teaching us. So let's go ahead and take a look at page 14. We're going to come back and take some notes later. We're just going to fill in some notes, do some examples, and then we are going to do the steps in a few minutes. So estimating square roots. We have perfect squares. What are perfect squares? Perfect squares are numbers whose square roots are whole numbers. Perfect squares we learned last lesson, they're always rational numbers. Examples of some perfect squares, hopefully you've been working on memorizing them, but let's come up with just a couple of them. The square root of 4 is a perfect square. 2 times 2 is 4. The square root of 64 is a perfect square. 8 times 8 is 64. How about, let's get crazy, square root of 196. Who remembers which that one is? Is it 14 times 14? Ding, ding, ding. Yes, it is. Okay, good. Non-perfect squares will always be irrational numbers. So examples on some non-perfect squares would be, let's say, the square root of 2. There's no number times itself that's going to equal 2. Square root of 6. Again, it's an even number. Some of you might be thinking, really, there's no number times itself that's going to equal 6? No, because 2 times 2 would be 4, 3 times 3 would be 9, so 6 falls between those. It's not going to be, there's not going to be a whole number that you can multiply by itself that's going to equal that number. Another one, just off the top of my head, 180. There's no number times itself that's going to equal 180. While the square root of a non-perfect square is irrational, we can use our knowledge of perfect squares to estimate their value. So we're never going to be able to pinpoint and say it's exactly this number, even taking it out to a decimal, because it's going to be a decimal that is non-terminating and non-repeating. So hopefully you remember some of our estimating work that we did earlier. And we're going to just do a couple of examples together, and then we're going to take some notes, and this should be a really short lesson. Estimate the value of the square root of 50. So we know the square root of 50 is not a perfect square. It falls between the square root of 49, which is 7, and the square root of 64, which is 8. So let's fill in the blanks here. Square root of 49 and the square root of 64. Now 50 is super close to 49. It's going to be the very next square root on the number line. So the square root of 50 is going to fall right there next to the 7. It's only 1 away from 49. Now the next part says 50 is how many away from 64? I'm actually going to nix that. That's not, I'm going to cross that out. That's not the way Eureka was teaching us how to do this. So when we were in the Eureka book, we took the difference between the greater square root and the lesser square root. So 64 minus 49. When I subtract 64 from 49, I get 15. So if I'm going to estimate the value of this non-perfect square, oh wait, what does this say here? Since 50 is closer to 49, the square root of 50 will be closer to 7 than to 8. And it should be just a little bit over 7. Okay, and I'm going to prove that now. It's going to be 7 and 1/15. This is our numerator. And the difference between the two perfect squares is our denominator. Now we learned also how to turn that fraction into a decimal. So I'm just going to do some long division. Let me move down a little bit further. I don't know if you have space at the bottom of your page or where your space is going to be good, but I'm just going to take it at the bottom of my page. My numerator goes inside, my denominator goes outside. Can 15 fit into 1? No, it can't, so I know it's going to be a decimal. And I'm going to add a 0 here. 15 still can't fit into 10, so I got to add another 0. Does 15 fit into 100? Let's take a look at how many times I need it to end in a 0. So I'm going to say 6. 6 times 5 is 30. Put the 0 down, carry the 3. 6 times 1 is 6, plus 3 is going to be 9. So that's 90, and I'm going to have 10 left over. So again, I'm going to have to add a 0 here, bring it down. So it's going to be 0.06 repeating. I'm going to be stuck in a loop here. So a good estimate of my decimal would be 7.06 repeating. If you notice, these are squiggly. They're not saying it's exactly that, but it's about 7.06 repeating. So the next one, estimate the value of 22. I will walk through this one with you, and then I'm going to have you pause the video and do 3 on your own. So number 2, estimate the value of the square root of 22. Let's see, it falls between two perfect squares. The one that's going to be less than 22 is going to be the square root of 16, and that's 4. The one that's greater than 22 is the square root of 25, and that's 5. So it's going to be between the square root of 16 and the square root of 25. Closer to 25, but it's still going to be 4 and some fraction or decimal. So let's take the difference between the two perfect squares. So 25 minus 16, that's 9, my denominator. I'll just call it a denominator, a den. The difference between the number I'm looking for and the lower perfect square, and that's going to be 6. That's my numerator. So my fractional estimate is going to be 4 and 6/9. Now I know how to change that into a decimal. So numerator goes inside, 6 divided by 9. It doesn't fit. So I'm going to have to say 60. How many times does 9 go into 60? 9 times 6 is 54. I think that's going to be the closest we can get. Okay, and 60 minus 54 is going to be 6. Oops, so I'm stuck in the loop. I can already see it. It's going to be 0.6 repeating. So my decimal estimate of the square root of 22 is going to be 4.6 repeating. Again, these are squiggly. So it's about 4.6. So what I'd like you to do right now is go ahead and pause the video. See if you can estimate the value of 103. Again, pick out the two perfect squares that 103 is going to fall between. Take the difference between the two perfect squares, and that's going to be your denominator. The difference between the number we're looking for and the lower perfect square, that's your numerator. You know what, once you get that far, go ahead and check back in and see and make sure that your work is correct. So go ahead and pause the video right now. Okay, check your work so far. So the square root of 103 is going to be between the square root of 100 and the square root of 121, closer to the square root of 100. Let's see, if we put it on the number line, we'd have the square root of 101, the square root of 102, square root of 103. Be falling somewhere around there. Okay, your next step, take the difference between between the two perfect squares, so 121 minus 100. That's going to be 21. That's your denominator. Take the difference between 103 and 100. That's your numerator. So if I'm estimating this, I'm going to say it is 10 and 3/21. I know how to turn 3/21 into a decimal. So my 3 goes on the, I'm sorry, I just wrote that wrong. My 3 goes on the inside. 3 divided by 21. Of course, it does not go into 3, so I got to add a 0. 3 goes in, or 21 goes into 30 one time. 30 minus 21 is 9. And another 0 and bring it down. Let's see, 20, 40, 60, 80. Let's try 4. 4 times 1 is 4. 4 times 2 is 8. So that's going to be 84. And 6, 20, 40, 60. It's going to be too much because it's 21, so it's going to be 2, which will be 42. And the difference here is going to be 18. Add one more 0. 21 going into 176. 20, 40, 60, 81. This, you're seeing me work this out, guys, and this is really how my brain is working, so I'm just saying it out loud of, counting by 20s to see if I can come close to what I think it's going to be. And I think this one's going to be 8. 8 times 1 is 8. 8 times 2 is going to be 16. Ooh, did I get close enough? I don't think so. Oh, I did. So it's 12 left over. Did I do that right? Yep, okay. So we've got 12. I think I've gone far enough because, again, we're going to have a non-repeating, non-terminating decimal, and this is going to go on and on forever. Most of the time, you're going to be told how many decimal places to estimate it to, and I didn't, and I just started going crazy with continuing with my my division here, and I apologize for that. If I've confused anybody, I didn't. That wasn't my intention. So this would be my decimal estimate would be 10, and let's see, 1428. Let's just go to 2 decimal places, 10.14. So I did all that extra work probably for nothing, and if we weren't so far into the video, I might consider redoing it, but yeah, I'm not going to. Next page. Why don't you see if you can work through these, because again, this is kind of a review. So which of the following square roots is best represented by point A, and point A is right here, and it's super close to 4. So you're going to want to estimate these and see which one would be closest to 4. Same thing here with which of the following would be the best estimate for the square root of 198. And then which 2 integers would these guys fall between? Bleh, I can't speak very well anymore. And then Rebecca bought a square table for her kitchen. The area of the table surface is 65 feet squared. What's the approximate length of one of the sides? So again, you have to set up the equation and then solve it. I will do these answers with you tomorrow in class, but for right now I want to go back to that notes page and I want to give you the steps of how to do this. Now some of you may have this down, so if you feel like you have it down, I still would, I like steps. So let's estimate, we can take one of the examples that we've already done. We'll say it's the square root of 50. Let's just add in the work here that would go with each of these steps. So determine which 2 squares the number you are looking for falls between. So that would be the square root of 64 and the square root of 49. Subtract the difference between your 2 perfect squares. Okay, we already did that and we said it was 15, and this is our denominator. Subtract the difference between the number we're looking for and the lower perfect square, so 50 minus 49. And that's 1. That's our numerator. And then we, of course, our fraction here is 1/15. Convert that into a decimal. And we already did this too, so we know it's 0.06. This is 90. So it would be 6 repeating. So we know that our best estimate of the square root of 50 would be approximately 7.6. 6.06 repeating. I know this is the example that we did first, but I wanted you to have it next to the steps so that when you're studying for it and you're like, I can't remember exactly how to do this, you'll have some examples. So we're right at 15 minutes, so I've got to wrap up the lesson, but this has been a review, and I would like you to do page, oops, my pages aren't numbered. Hang on a second. So I want you to do page 15 for sure, and of course do your summary, and then work on page 16, and we have a different worksheet too in class. So I will see you tomorrow. Have a good night.